Good day to you on the third day of June 2026. In the back here on our high-tech whiteboard, you can see the name of my channel, AE. Type in a space and another word, Anagalactic. Anagalactic. It had its time back in the 1920s. Really means supergalactic. Anagalactic is my chosen term for my station, but it's not its name. But if you type in both AE and the word Anagalactic, you'll find my channel. I'm forced to say this because so many people have reported to me that they just couldn't find my station. They type in AE and all they get are these nursery rhymes for learning the vowels. I'm very low on the totem pole. I'm not really very well known by the search engine. I'm what's called deprecated. Like you'd have to go through hundreds to even find me. So I tried to find myself. After so many people told me, I can't find your channel. And so I tried to find my own channel. I couldn't find it. But as soon as I typed in the word Anagalactic following the letters AE, then it finds it. Today we're going to go back in the Wayback machine a couple of years. I've only been producing for 4 years on YouTube. I have made over 1,600 science videos, which really got very few views in the first couple of years. I was so unpracticed. I'm really not a technologist. I don't really do this sort of thing. I'm not gifted in this area. And you'll see that I blunder along trying to show you things in inset windows when I don't even know what I'm doing. My delivery was not polished. It's a lot more polished now because even a dunderhead, if you keep practicing, you'll make it. It just may seem like it'll take forever. Now you have to be aware of your goals. Some goals are unachievable, and it could be due to some lack in you or me that we just can't do mathematics, for instance. That's very common. And so really, there is a problem with approaching science from the mathematical side. I had begun to achieve a modicum, a threshold of proficiency where I was starting to wear a tie, for instance. So out of the 1,600 videos I have produced, you'll only be able to find 500 of them that are public. Fairly carefully gleaned. It took a while. What I'm doing here is going back through those videos and selecting the ones that got quite a few views, relatively speaking. Again, I'm not high on the totem pole because I'm not trying to make money. But every single other producer, other than people who just make music videos, extremely popular. These people are not asking for money, they're artists. That's kind of how I started. Really, you have to do this for yourself. I believe that that is just the way it is. You're doing science in order for you to get something for your life. If you're not doing that, you're not doing it right. You're probably doing it for money. Money is absolutely poison to science. You have to replace the word money. We take it for granted. You can't. A scientist doesn't take anything for granted. Now, I know I'm preaching, but the reason I'm doing that is to let you know that I do take what I would call, I suppose, in an extended sense, a religious outlook on science. It is for human answers. We're at the cutting edge. But why are we doing that? Don't make up a myth. We're not going to the stars. We're not going to meet the aliens if you have that kind of a religious outlook. That's not going to happen. You're going to live and die on this planet the same as the 8 billion living people and the 8 billion dead. That's a pretty accurate figure. The history of mankind only goes back 10,000 years. We know the age of the Earth. It's the same age as the Sun, obviously. So that's about 4 billion years. We know the life cycle of stars. And so we do know how old the Earth is. But how long has it had an ecology? You have to answer that question. And you have to answer it first, because it affects you and your future. How you regard that. It's not millions of years. The ecology has only been here for less than 20,000 years. That's been proved. And you have to find that out for yourself. You have to know that. It's not a belief. Scientists don't believe things. We certainly don't believe each other, and we never believe a theory, ever. The Big Bang is a theory. It's been disproved. So what is the true structure of the universe? It's not the Big Bang, although the Big Bang is a very important theory, and I'll be discussing that, why it has relevance. But as for it coming from a zero dot, no, that's linear. I'm going to be teaching you geometry that has a central number that is not zero. That's our 10-minute introduction to this Wayback Machine production, You're After Truth. Thank you for tuning in. We'll be right back. Good evening to you. This is Anagalactic on the 4th day of November of 2022, broadcasting from Chico, California. The Dirac equation is legendary now. If you don't know anything about it, don't worry. Nobody does. Only Paul Dirac knew anything about it. And he's gone now. But I'm going to teach you how to read this stuff so you'll actually know what these things are trying to say. The knowledge is in there, and I'll show you where it is. But look at that equation. That equation looks like it's a well-formulated equation. It is, as long as you know what each and every one of those symbols means. And once you do, which will take you 16 years, and I'll show you a quote where it says that. It actually says you're going to need 4 years of advanced calculus to understand this equation. I'll show you what it means in under 10 minutes. First of all, you have to know how to read it. And it's fairly simple once you have a kind of a guidebook where to start. You start here on the right-hand side. This thing, the squiggly DT, you can scratch it out. It doesn't mean anything. Technically, it means a partial derivative. But that is implied, and it doesn't need to be there. There are 3 terms on this side. You can erase these 2 D's and this T and take this line out of here. This is called psi. It's a function. Technically, it's the result of the function. But you'll notice that the function is on both sides, and so this is an identity equation. And the reason I say that is this psi is in the numerator. So this is the imaginary number, this is the reduced Planck constant, and this is the function psi. On this side, we have the function psi and a coefficient for it. There are only 3 terms in this equation. Psi, psi, and the coefficient. And now I'm going to tell you how to read this. The I means imaginary. This means reduced. It's actually not difficult once you know what these poor men are forced to. It's the linearization of a spherical function. Actually, a spherical system. And it is spherical, they know that. But here's the problem. All of these scientists are convinced that linear algebra can reach this kind of thing. Obviously, it can't. I'm going to show you why not, and the solution to all of this in understandable form, and the Einstein field equation, which is much easier than this, I'll say. This is the imaginary, reduced, linearized psi function, which is actually a 4 number. It's a 4D number. 4D means it has 4 numbers in it that are all linear numbers because they all represent orthogonal lines. And the 4th one is the killer because it's imaginary. And that's why you have I. You're always going to have an I in these equations somewhere because of the ridiculous way that Einstein was forced to make this linearization of spherical space. He had to invert the valence of the time axis. So it has a negative valence, whereas the spatial axes are positive. That destroys any hope of understanding it. Not completely, because it has to have a geometry or it wouldn't work. I found out how it works. You may already know it's hyperbolic geometry for the Einstein field equation. What is this? Well, it is also a 4-axis system. It's called a 4-component number system. And Paul Dirac used a very famous shortcut, which you're always allowed to use, called complex numbers. Now, all of that is hidden in here. It's like the Einstein field equation. You look at it and it's just about this long. And you look at it and you think, well, it couldn't take too long to learn. That's what I thought about the Einstein field equation. Yeah, it takes a long time just to learn what it even says, let alone what it means. But I've become quite adept at doing this. This is the imaginary, reduced, linearized psi. So you could also say this is the imaginary, reduced, derivative of psi. This on the other side is just psi. So this is the relationship between psi, which is a value. It's a 4D value. And it's equivalent to the derivative of that value on this side. So this is the equation of equivalence between the psi function and its derivative. For the derivative of the psi function, it's the imaginary reduced form of psi. On this side, it's not imaginary, it's not reduced, and it's not derived. This is integral psi with respect to this psi. Or you could say that this is the derivative psi with respect to this psi. But the relationship between these two is the calculus. It's the calculus relationship. It means there's a relationship between this side and this side. And on this side, you're taking a calculus derivative. You can invert that because the fundamental law of calculus is that the integral is the exact inverse of the derivative. That has been argued for 3 centuries, and if you wish to join in, spare me. And I'll try to share that with you so you can be just as pompous as I am. All right, so this is psi, and this is the derivative of psi. And that's all this is the derivative of psi. These are the converters that make it into the right form to match this side. So when you take the derivative of psi, you also have to reduce it and then imaginify it. And once you have an imaginary reduced derivative of psi, you can use this to find out how this turns psi into its derivative. So this is an extremely valuable function because it establishes a relationship between the psi function and its derivative. Now, what is the psi function? Oops, I keep doing that. Let me put that back. What we need, you don't need to know what's in here because it's inside of these. Those are called braces, or parentheses in American English. I think that's international. So the psi function on space and time is a complex 4-component field that Dirac thought of as the wave function for the electron. R and T are the space and time coordinates. The R has 3 spatial components, and the T is negative time, as you know. That's called the Einstein signature. I'll show you that there are about 16 names for that signature because this is an extremely confused, convoluted, absolutely uncoordinated, basically leading nowhere for 70 years. You could make it 100 years. And this actually does not ultimately help. Although it will once it's translated into the right geometry. All of the progress that we've made, both in cosmic science, which is astrophysics, you can exclude the cosmologists. They're simply guessing. Astrophysicists are not guessing. They're taking educated guesses. The cosmologists are not. They're taking uneducated guesses. And you never want to dabble in cosmology because it's never right. But astrophysics, although it hasn't been able to get very far, at least it has the facts and at least it has the knowledge. So far, no one has any understanding of deep space science. None. None. They don't know what to do next. And it's been like that for a century. Zero progress. And there can only be one reason for that. A fundamental mistake in the way we've approached the universe. And I'm going to show you what that is so I don't have to keep saying it. I'm going to show you. This right here is the coefficient of psi. This is psi equals the derivative of psi. Now, psi does not equal the derivative of psi. You're going to have coefficients. And that's all this, and this are. They're coefficients that equate the psi function with its derivative. And I can now state what this says. That whatever this does to psi, on the other side, for the derivative of psi, it will equal the imaginary reduced form of the derivative of psi. The imaginary reduced derivative of psi equals psi times this. That should be valuable, but before it could be valuable, you have to know what it means. And nobody does. So, the rest is just explaining what nobody understands, so that you'll know what they don't understand either. And here, this tells you what alpha is, that thing right there. Look at that. Alpha is composed of these three components, each of which is a 4x4 matrix. And beta, this one, is also a 4x4 matrix. But look at that alpha function. This is momentum. There's no need for you to spend 4 years to learn that. You know everything that they know about it. I just told you what it means. The algebraic structure had been created by Clifford, emerging from Grassmann's Die lineale Ausdehnungslehre, a legendary book. This is one of the most remarkable chapters in the history of physics. That's absolutely true. Is that Dirac got this from Grassmann. That was a century before Dirac. Clifford lived in the 1870s. Die lineale Ausdehnungslehre was published in 1844. Dirac is explaining a relativistically moving electron, another not understood anything, consistently with relativity. You see, that's what they're actually trying to get. And Dirac made a major insight, but it's written in linear algebra ease. It's written in calulasite. It's written in calculesia. It cannot be understood because it's not understandable. So this is the most important statement in this article, which is from a blog site, which I'll give the link for that. Discretizing the angular momentum of the electron's orbit had failed. That is the problem. That is the only problem. And it's well stated, and this also affects the Big Bang theory, the black hole theory, the theory of galaxy evolution, and everything else in astrophysics, and everything else in atomic physics. Everything is affected by this. Is that the angular momentum value cannot be computed. They can't do it. Everything is based on angular momentum. Everything is based on angular momentum in the whole universe. Angular momentum is the direct expression of energy. Max Planck proved that. But you notice it's angular. You know what that means? It means it's not linear algebra. And you might think, well, maybe we should just change to the right algebra. You would be right. What would that mean? Well, it would take a really remarkable discoverer to find out the correct algebra. I did. That's what I discovered, is the correct algebra. So, the quantum mechanics of Heisenberg, Pauli, Jordan, Schrödinger, and Dirac himself had made no progress. It still hasn't. His equation had far deeper implications for the structure of matter So they think, and introduced new mathematical classes of objects. That's correct. It made it way, way, way more complicated. Just as the simple definition of gravity resulted in the most impossible to understand equation of all time, Einstein's field equation. But it's a tie. Dirac's equation is equally difficult. And they cannot be understood. They cannot be understood. So why are all of these equations being written? It's because we know we're close. But it's going to take a genius, someone who does not look like me or sound like me or do what I do. It's going to have to be someone other than myself who makes this discovery. But alas, it's too late. I got it. Now this is another page. I just want you to see this. All right. Oh, it's tetrahedral.blogspot. Okay? So there's our equation right there. And here's how to read it. The right side can be, right, gone through that. So I'm going to go down here. Right here, time space. I abbreviate a lot of things in my writings. Small t, capital S, that's called camelback, and it means time space. There are, in time space diagrams, are 4D diagrams, which you can imagine you'd have to really be clever. It can't be shown, but it can be projected down to a 3D. And from that you get what's called the light cone, and then you have 3 different intervals. Time-like, light-like, and space-like. Don't worry about understanding this. Classify 1D curves through curved space-time. Similar to the error missed in string theory. Okay, this line here, the error of dimensioned linearity, that's my discovery, and this one, the error of assumed linearity. These are the 2 mistakes that describe all of physics today, are based on these 2 errors. When I compare time-space with the string theory, that needs to be explained. The string theory is considered now to have missed the mark. We all knew that at the beginning, but nobody knew why it would miss the mark. It just smelled wrong, and sure enough, now it stinks to high heaven. Nobody gives a hoot about string theory any longer. Why? Because it's no different from space-time. It's a reformulation of space-time, making the same mistake that was made in space-time. You're trying to bend a straight line. That's all you need to know about string theory, and that's all you need to know about space-time for now. Space-time, however, is a much different animal. But the error that was made in string theory, I call the error of dimensioned linearity. In other words, a line is always straight, correct? Well, what if you try to pluck it? I actually made this mistake in part of my research last spring, and it took me a while to come out of it before I realized that I was making the same mistake that the string theorists had made. I was trying to establish a harmonic on the sphere by a pluck. Well, that actually changes the sphere. Now, it might be physically true that the sphere is not exactly a perfect sphere, but currently we have no reason to believe that. And so that's a red herring. But it's interesting to notice that I made the same mistake that the string theorists made. This matter of the time-like, light-like, and space-like intervals of classical space-time, this is what all of them use. All of the astrophysicists use this space-time interval. It's wrong. But why is it wrong? It's because it's linearized. It's linearized, and 4D is the wrong answer. And so they're using the wrong geometry. They're using 4D. 4D cannot work. It's 4 lines. These aren't lines, children. This cannot be linearized. And so that's the mistake. Now, there's another mistake called the error of assumed linearity. Well, actually, I should tell you what that means. Why am I citing 2 different errors? They're closely related. When you're using a straight line, that has all the numbers on it. When you compose space or you try to compute anything, you just add more lines. When we're done, when we had 3D, that lasted 2,000 years. But then Einstein used 4D to get the definition of gravity. And both of those are the linear solutions. And that's why nobody can understand them. James Maxwell used 4D to compose electrodynamics. That works for electrical engineering. And that's all it works for. Because then you can use calculus. These 2 errors of mistaking the linearity of the system for something that they can fix leads to the Erlin-dim and Erlin-ass. And if you put them together, that's dim-ass. And so the way I pronounce that is airliner. In other words, if I catch you, which I've caught them all, using linear algebra to compute quantum mechanics or astrophysics, then I get to look at you and laugh and point my finger and say, well, I guess you didn't go to school then. That's a real airliner. A real airliner. I have a vendetta. I'm trying to get rid of it, but it's going to take a while, man. I admire each man individually. They have been struggling like trying to swim up a waterfall. And they've worked miracles in trying to get sticks, Greek sticks, to explain things in heaven. Only a monkey. Presentation in a series on geometry. Geometry is a widely known subject, and so it behooves me to state a little bit more about what I am doing. What am I doing with geometry? My premise in science is to study heaven. This is one of 2 courses, obviously, where the other one would be Earth. Earth and heaven are obviously related. They are given 2 different names for a specific reason. We dwell on earth and will never get to heaven. Now that raises a question in our minds as rational men. So the subject of my lecture, and continuing until the solstice, will be, what is our position in the universe? It begins, obviously, on Earth. But that leaves open a very wide field, which is basically everything over our heads. This would be traditionally the study of astronomy. That is the correct word, and that is the way I use the word. The study of heaven. Heaven has a history which perhaps is objectionable from one side of any person. I myself am involved in this dichotomy where we are talking about heaven as if it were something separate from the earth. Physics teaches us otherwise. And so the course of science brings into communion, into correlation, our position on earth with our position in heaven. And that raises a question which has a structured answer. And that science is called geometry. In the study of astronomy, the subject of trigonometry comes up. This would be the use of our linear system, basically our system of vision, where we produce our visual perceptual space and onboard system with which we were born, we see linearly. We have 2 eyes in the front of our head,
which are able to produce a parallax, two straight lines converging on a point. From that, we can get a midpoint between our eyes. That's putting it perhaps dramatically, but that is the essence of geometry, is trigonometry, from Greek, which means three. Three lines making a triangle. From this, we have derived all of science, and there is no aspect of science that is not touched by geometry. It is the highest calling in mathematics, and mathematics is a tool of geometry, and mathematics is a slave. Mathematics has achieved the position of godhood because of technology. That is an extraordinarily imbalanced situation, talking about Einstein's spaceTime, which now is the dominant geometry. It has been so shot full of holes from every direction that no matter what your religious outlook is on space-time, the geometry of the universe, if you're a PhD or a Nobel laureate or you have some other accreditation, you are fully entitled to sit in on this lecture. But I am not talking to you. This is for high school age. My subject is geometry and the universe. The way we're going to begin is with this man, Roger Josip Boscovich. He was a contemporary of Leibniz, who was a contemporary of Newton. Roger Josip Boscovich is coming back into the front line of science today. He achieved an expertise in geometry which has not been surpassed by the astrophysicists or by the quantum mechanists. And that's why his name is starting to come back up. I'm currently reading his book, and from now until the solstice, I will be involving you as well as myself in the amazing production of Boscovich's curve. This is your first lesson in geometry. All of you high school students of the future, this is about curvature. And your first lesson in geometry is that a curve is not straight. I hope you can grasp that.
But that is the problem.
You will notice from this painting, and it is an oil painting with a very bad granularity, 2.5 centuries ago. I want you to notice that he is sanpaku. This is a Japanese term for when your eyes are always pointing up. According to the Japanese theory, his name is spelled in Croatian and in Italian and in French, and then now we have it in English, and we're not sure what to say, but his first name is Roger. It's Ruger. And I'm sure I'm mispronouncing it because I'm not Croatian, he is. And he spoke Croatian and several other languages, including Latin. I'm reading his book in Latin. No, it is in Latin. It's on every other page. And I'll give links for where this book may be acquired. Boscovich is now rising back up into the limelight right along with Dirac, Einstein, and everybody else, even though he lived so long ago, is because he discovered a geometric relationship between particles which defines the electron orbital shell system and pretty much everything else in forces. And so his theory, when you sum up, he would say this too, he would agree with me, this is his theory. It's a theory of forces. And that is not how anybody looks at the universe today. And so I'm going to be covering very quickly this evening a brief recount of how we got to the situation we're in science at the two cutting edges, going out and going in. We're trying to find the building blocks inside the atom, whatever we can find in there. That's quantum mechanics, by the way. And going out the edge of the universe, the galaxies, the superclusters, the black holes, everything else. Pulsars, well, those are stars. Quasars, which are not stars, they're incipient galaxies. Gamma ray bursts at the very edge of the visible universe. There are things that have not been discovered yet, but we've already identified the cosmic microwave background radiation, which, for your information, and you can take it from me because I've been studying this for 15 years, the cosmic background radiation is predicted by any theory. No proof of the Big Bang at all. Fuzzy light at the edge of the universe, which is, oh crap, are we excited about that? There he is. Isaac Newton. Rather famous, I don't really need to fill you in on anything about him. It shows him as being somewhat human. It's pretty obvious that he has no chin, a very long nose, kind of bulbous eyes. He's a normal looking man, there's nothing wrong with him, but I think you've seen other portraits which were done by professional painters where you could just hear the conversation in the background. Now, Sir Isaac, I'm going to paint you with a really strong chin, a nose that's not quite protuberant, and your eyes, instead of just being like oysters swimming in a dish of cream, going to make you with a penetrative look like you're looking into the future with a really strong chin. That guy really changed a lot. Why? Hyperbolic geometry for the trajectory of planets on an orbital path, capitalizing on the discoveries of Kepler. Newton systematized it into a hyperbolic geometry of the third order. That is also coming back up for review because Sir Isaac had some presuppositions that Boscovich picked up on. Sir Isaac was contemporary with Leibniz. They both invented the calculus. It's obvious that Leibniz got it right. Newton kind of got it right, but he knew what to do with it. First of all, I will teach you calculus because there's only one right way to learn calculus, and apparently I'm the only person who realizes that. I will teach you calculus. You need to have the right geometry. Now we're back on topic. Let's go to the next guy. I'll have to switch over here. We've covered two men. Let's get a look at Gottfried. There he is. That's Gottfried Wilhelm Leibniz. Now, I said it wrong. Leibniz. You may encounter a problem spelling Leibniz's name because the sound at the end is ts. Shouldn't that be two letters? In German, it's just one, a Z. But in English, you will see it spelled Leibniz with a TZ at the end. I'm just saying that. Now, doesn't he look like Bach? Johann Sebastian Bach? He kind of does. He looks even-keeled, doesn't he? He doesn't look intense like Newton always did or tried to. He doesn't look dreamy-eyed like Boscovich. Boscovich, by the way, I meant to mention this, he was a priest, and a very good one. Boscovich was a member of the Jesuit Order of the Roman Catholics, as was fairly common in Europe at the time. And he was a goddamn priest. I mean, I respect Boscovich enormously, and my opinion of the Catholics has been going up and up and up since I was brainwashed by some Protestant organization I won't name, the goddamn Seventh-day Adventists, who fucking hate the Catholics. Well, take a look at their record. They don't even have the Sabbath right. Ha ha! And their whole name and identity is based on getting the Sabbath right. Just a little background on how I get so emotionally involved with that. I was a Seventh-day Adventist for 15 years, and I tried to point out that there are 7 Sabbaths, and no. And that was bad enough. They kind of shunned me after that. But I kept going, and I became a missionary for the Seventh-day Adventist Church to Ukraine. So I went there and lived there, and then things happened. The CIA got involved, I think. And the school closed down, so I lived there illegally because I was in love with the princess of Ukraine, who was 19 years old, and I ended up marrying her. But that's a little history of my involvement with Ukraine. So now our next guy that we want to visit. I haven't said anything about Leibniz. He had not really a very good geometry, but what he did have was a very good calculus. Also, he had a theory called continuity. And every single one of these men has some aspect, some part of their theory has to deal with continuity, which we'll be talking about. It's a geometrical concept, and Boscovich picked up on it. And that's all we'll say there. The next guy we've done, here he is, James Clerk Maxwell. Now I say Clerk because that is a C-L-E-R-K, and some men's names you just always give his middle name. And everyone always gives James Jimmy's. He was a Scotsman. I love this portrait of him because it doesn't look anything like any of his other portraits because he grew this gigantic, fucked up beard that made him look hideous. And then he died of stomach cancer at a very young age. So that's James Clerk Maxwell. What is the significance of his role in what I'm trying to present to you about the universe and about geometry? He came up with some equations for light. And this was, it's very well known now. It's called electrodynamics. One of the most, and I warn you away from that. Do not try to study electrodynamics if you want to have a normal life. Because if you start to study electrodynamics, first of all, your chances of getting through the course at the graduate level are about 40%. And if you do make it, you'll probably be a millionaire. So there is a great incentive for learning electrodynamics. But of the 60% who drop out, there's a certain fringe group that they lose their minds because they know they have to get through this or they'll die, and then they realize they can't. And that can happen very easily. That also can happen at several levels. I'm going to protect you from that. You do want to study these things, but what you don't want to do is get into the mathematics too deeply. Because if you do, you'll be lost to the way of heaven. And that is what I talk about. I am a priest. I'm more of a priest, or at least as much of a priest, as Roger Boscovich, or anyone in the Catholic Church, or anyone in any church. I'm a scientist. I'm supposed to be a priest. Supposed to be. What does that mean? Is to guide men to heaven. Isn't that a good definition of a priest? Guide men to heaven? Well, the only men who have ever guided men to heaven have been astronomers. Okay? That is your first lesson in geometry. You want to know geometry? You better know what it's for. The mathematics is a tool for geometry. All right, I'm mounting my pulpit, so let's not do that. So I'll get back here and we'll go on to our next fellow. We want this guy now, Max Planck, and this has a quotation on it, which I'm pretty sure you can't read, but let's see if we can just do something. Oops, oh dear. I want to be cautious here. I'm not too technically wise yet, although I will be. Did that help? No, because it's not on top. Well, I think you can see the whole quote. Science cannot solve the ultimate mystery of nature, and that is because in the last analysis, we ourselves are part of nature, and therefore part of the mystery that we are trying to solve. He just contradicted himself. I hope you noticed that. It's actually a circular argument, but I want you to look at his face. Does that guy look like he's been through some shit? If you want... We moderns, myself, I am a perfect example. this just baffles me every time I read the lives of these guys. You get interested in the scientists themselves. Max Planck's life is just an endless series of tragedies. He just died a very, very unhappy man. And yet he made the greatest breakthrough in the history of geometry. And it was a discovery in mathematics. And he didn't think it was geometry or mathematics. He thought it was physics. But what he discovered, I discovered some things about what Max discovered. And his major discoveries, there are two. One of them is the counting number system for universal mathematics. The counting number system that the universe actually uses. And his second discovery is the equation of light. This goes so far, and he did not believe that he discovered any of what I'm saying. What he thought that he tried to deny that he discovered anything at all. He didn't want to discover it. He discovered the quantum. And what I discovered is what the quantum actually is, geometrically. That is a major discovery, but I'm not here to toot my horn. Let's go on to the next guy. And here he is. That's Paul Dirac. The reason I chose this very unusual and rare photograph of the young Paul Dirac is that it shows him as a normal man. Paul Dirac was considered to be, by those who met him, quite an eccentric sort of a person in a morbid way. He avoided people. He really wasn't very communicative in a certain social sense. He was just a loner. He turned people off. Some people said he must be autistic or he was just a weirdo. Let me tell you something about Paul Dirac. He was none of those things. He was the most cultured, gentle, wonderful man, but he had a calling. He was among four men, 4 or 5 or 6, it's hard to say, it's the beginning of quantum mechanics. He got the correct, or mostly correct formulation of the quantum mechanical waveform under relativistic mathematics. That was quite an accomplishment. And there are several versions of quantum mechanics. The Schrödinger version, the Heisenberg version, there's another one, and there's Paul Dirac's, and that stands alone. And it is definitely incorrect. That has been demonstrated conclusively by a modern astrophysicist. He calls himself a mathematician, Dennis Morris. Shout out to MR. Thank you for your comment. From watching Dennis Morris's expose of the Dirac equation, I came to realize just exactly why Paul Dirac is legendary. And that's the end of our sequence. I don't have a photograph of Albert Einstein because I think you know what he looks like. Probably the most famous man who's ever lived on the face of the earth, with the possible exception of you fill in the blank, because you know the beauty pageant thing. You're never right when you say someone's the best or the greatest or the... Sometimes you're right when you say the first man, but when it comes to quantum mechanics or astrophysics, you're rarely right when you name a man. Everyone stands not on the shoulders, but on the database of what came before. So, we're now at a half an hour, and I would like to switch back now. It's going to take me a moment to do this, but I'll keep talking while I'm doing it. So the subject of this, we're going to cut this off at 40 minutes mercifully so I can edit this somehow. Gravity and light. When you want to study the universe, you want to study mathematics, you want to study geometry, you want to study reality, finally you're going to get down to two things. If you're studying astronomy, you only have two ways of doing it: gravity and light. We will never touch the universe. We're not going to send probes there. We're not going to land there. We're not going to the stars. We're sitting right here on the spherical surface of the Earth looking out through telescopes. But it's pretty obvious that the Earth is controlled by a force called gravity. We've also found out, believe it or not, the sun has gravity, and that's why the planets go around it. We've extended that after Hubble discovered what galaxies actually are a century ago, not long ago. Those have gravity, but that gravity has never been understood. That's a remarkable statement, that galaxies do not obey the law of gravity. And this has caused a you-know-what storm. We'll be covering that because you need to know some things about basic geometry and basic forces. Now, when you're talking about gravity and light, you're talking about force. Light goes out, correct? Light never comes in. We think of it coming into our eyes, but that's because it went out. Where did it come out from? Where does light come from? It comes from electrons. Electrons produce light. That is a simplification because I didn't state it geometrically correctly. But basically, a ballpark statement, if you had to just sum it up, it comes from electrons. And those electrons are in stars, and stars give off light because the electrons release what we call photons. Photons are a highly controversial object. They're accepted by the Standard Model, but I'll tell you why they are accepted as such, although they're not anymore, and cannot be, and never will be again. But for the longest time, photons were a major issue. And they're still called photons, and you can call them photons, but unless you know the geometry of what you're talking about, you will never accurately understand or portray what is a photon, because we know now it's two things, but nobody can distinguish between them, because one of them has to do with geometry, and the other one has to do with geometry. But the problem is they're two different geometries, and mankind has only discovered one geometry. Unless you include me, Scott Allen Miller, whose name will never be attached to this if I get my way, but your name might be attached to it, the second geometry that was discovered in 2022. The geometry of the sphere. And light obeys the geometry of the sphere, spherical geometry. Nobody knows that yet. And that is the problem. And the problem that you're going to face as high school students when you study geometry, as I'm going to command you to do, because it's your only rational choice, is to study geometry. Now, you will have to study everything else as well. I'm talking about focus. I'm talking about orientation. I'm talking about understanding. Do you want to understand the universe? Then you're going to have geometry. Because the only way that the universe can be understood is geometrically. It cannot, and let me repeat this so you hear it very well. The universe, beyond the solar system, okay? Whatever is the starry realm, it's 1 billion times bigger than anything we knew a century ago. All right? So this is very important. That billions of times bigger thing that we call the universe is geometry. It's geometrical, and we need to understand the language of the universe, which is geometry. Is it mathematics? I will prove to you that it is. But is it linear mathematics? I will prove to you that it is. But if that's all you know, you can join the ranks of the current astrophysicists and quantum mechanists who will never understand the universe, ever. Because unless you understand the other geometry, which is not linear, you won't understand the universe. Period. And that's 40 minutes. The lab cat did not pay a visit. I hope you've had a chance to read this, but in the next lecture, I'll be expounding on what's on this page. And that's exactly 40 minutes. This is Anagalactic, broadcasting to you on Friday, January 27th. With the first, it's lighthearted for now. I haven't borne down yet, but in the upcoming lectures, you're going to be tested to the limits of your ability to understand anything, because I'm going to force you to see. That is what a priest does. We'll be right back. Stay tuned.